ZBOT is a space experiment. It's a science experiment performed in the International Space Station in support of cryogenic fluid management of propellant tanks in space. It's a science experiment because it studies fundamental issues of phase change, fluid flow, heat transfer that affect preserving and keeping fuels in depots in space. ZBOT is important because it's a step towards designing this zero boil-off tank control system without which you won't be able to do the long duration expedition. For long duration missions, you have to be able to fuel on orbit, preserve these fuels, which could be hydrogen, methane, oxygen. All of these liquids have to be preserved in space under very low temperatures. Hydrogen, for example, has to be preserved at 20 degrees Kelvin. That's very low temperature. So small heat leaks from the environment, radiation on the tank surface, can penetrate the heavy insulation that's installed on the tank. And once the heat goes in, it starts evaporating the liquid. These tanks are also supported by some support structure. Conduction through these support structures also can cause localized heating of the tank, and that localized heating can instigate boiling and evaporation in the tank, which again means the tanks would be pressurized. The physical phenomena that happens in the storage tank is very complicated. It requires solving the energy, the fluid flow, the species, and the mass equations in the tank under conditions with the flow is very orderly, which we call laminar flow, or very chaotic, which we call turbulent flow. This requires solving these equations at many, many points in a computational grid. So as a result, for simulating like a pressure control situation, a mixing control in ZBOT, you might be solving 50 million simultaneous equations. With 800 processes working, some of the simulations take over a month to perform. We had a few interesting results for ZBOT. So let's start with self-pressurization, because those were the first series of experiments that we made. When we self-pressurize the tank, heat goes from the wall into the tank and causes the temperatures to rise in the liquid and the vapor, and evaporation takes place, the pressure rises. Sometimes during self-pressurization, boiling can occur at a hot spot on the wall. This causes undesirable pressure spikes in the tank. Because of microgravity thermal stratification, boiling happens more easily in space than on Earth. It was interesting to note that the trend in microgravity, although a lot of things, including the olive shape, which is the bubble shape, the vapor shape is different, and the amount of convection is different, the trend followed the trend that we observed on Earth. That's an important finding, because it says that we can use the Earth data as a conservative estimate of what pressurization would be in space. And for the first time, ZBOT was able to obtain this self-pressurization data in microgravity, and we were able to validate our models against that data. During the pressure control studies with the forced jet, we found out that actually we can use the forced jet at very low velocities, at very low speeds, to position the liquid where we want it to be. The follow-on experiment to ZBOT1 is called ZBOT-NC. It stands for ZBOT non-condensable. What happens in a real tank situation is when you want to feed the engine, you want to pressurize the tank very fast. So that's often done by injecting a foreign gas. Like in a hydrogen tank, you inject helium inside. Helium doesn't condense at the temperatures of hydrogen, so it's referred to as a non-condensable gas. Then you can feed your engine, the pressure drops. Now you have to store the fluid, which is a mixture of hydrogen and helium. When the tank pressurizes, again, because of heat leaks from the surrounding and the pressure goes up, with the helium present there, you will find out that you don't have the same capability to bring the pressure of the tank down by cooling the liquid. The non-condensable forms a barrier to that process. ZBOT-NC is studying the effect of non-condensable on the pressure control strategy.